Alright gang, here we go. This is Chem 2, Unit 1, second half of Chapter 1 material. For those of you just joining us, this is from Brown and LeMay, 14th edition. Alright, so last time we last time we finished talking about separation of mixtures, we talked about filtration, column and paper chromatography, and we talked about distillation as well. This time we're going to move on to measurements in chemistry and wrap up the whole thing by talking about sig figs and dimensional analysis. Alright, so this is a little beefier video than the last one was. Okay. So energy is the capacity to do work or transfer heat. Alright, so anytime we're transferring energy that makes something do work, meaning like move a piston or move something a distance or something like that, then we're using energy to do it. It's also a transfer of heat. Okay, and that's primarily what we care about in chemistry, is transferring heat from one thing to the next. Okay, work is defined as the energy transferred when a force exerted on an object causes displacement, right? Work equals force times distance. If you take in physics, then you're probably very familiar with that. All right, and then heat is the energy used to cause the temperature to increase, all right, or decrease. And so when we talk about heat, we're really talking about energy flow. All right, and then the force is any push or pull on an object. So the reason these terms are included is just so when examples are used throughout the textbook and in subsequent slides, that you're kind of familiar with some of these terms. None of this stuff is really going to be tested directly in this class. It's just going to be, well, some of it will be, but like work and force, those aren't really going to be tested directly. We will talk about heat and talking about energy, though. All right, there are two fundamental forms of energy. You've got kinetic energy. It's defined as the energy of motion. Okay, the energy of motion, and classically it's defined as 1/2 times the mass times the velocity squared. All right, so you can figure out how much kinetic energy something has by taking its mass times its velocity squared and dividing it by 2. All right, so it's the energy of motion. Potential energy depends on its relative position compared to other objects. All right, so there's lots of different potential energy types. So it's kind of like its ability to do energy, or to be ability to have kinetic energy, if you will. Like here, specifically, it's this biker that's going downhill. Here she has high, and we're going to call this gravitational potential energy. Right? And then as she goes down the hill, the gravitational potential energy turns into kinetic energy. There's lots of different types of potential energy. There's spring potential energy, like imagine you have a spring that wants to be like this, but you grab each side and you stretch it out. So it's like this. That spring wants to come back in this way. So when you're holding it out, it's got potential energy, right? That's how like old time clocks work. They used to have to wind, or like metronomes, they go tick tock like that. You have to wind those, and you're really tightening a spring, getting it out of its equilibrium, so that you induce and you start it to hold back some of that energy. Okay, and then primarily in this class we'll be talking about kinetic potential energy. So we're talking about the energy that could be released or taken up when you make a chemical reaction take place. Okay. Numbers in chemistry, big deal. We like to do measurements in chemistry. Okay, and lots of things are going to be quantitative, meaning that we're going to take actual number values. So this is still a little bit of qualitative chemistry that goes on in Chem 2, but comparative to Chem 1, there's a lot more number or quantitative chemistry going on. Okay, so we're just going to briefly talk about all of these things today in this video. All right, we're talking about units of measurement, quantities that are measured and calculated, uncertainty in measurement, significant figures, and dimensional analysis. So that's kind of a checklist of what we're talking about. Okay, in Chem 2, we're going to use the SI units, okay, because we're scientists and not barbarians. So we're going to use the SI units for calculating measurements and all this stuff. These are the base units, the SI base units. There are 7 of them. Okay, some standout ones that are more different than what you'd expect. Like mass is the kilogram, not the gram. Okay, so that kind of throws people for a loop a little bit. Remember, your temperature must always be in Kelvin. Okay, we'll talk about what difference between Kelvin and Celsius is here in a bit. Time is in seconds. Mount is in moles. Okay, we're going to do moles a lot. Electric currents in amps and luminous intensities in the candela. We're never going to do anything with those two things, but they're, Jeopardy knowledge. It might be worth knowing. Okay. They use these base units. And then there's also, let's see, this guy here is actually a derived unit. Okay, so this is a derived unit because it takes the meter and cubes it, right? Because if you think about it, if you have a cube and you want to find the volume, then you take the length times the width, times the height. Yeah, I kind of fouled that up, didn't I? But that's okay. So length times the width times the height, and that gives you the volume. So this is what's called a derived unit. Derived units are things that are made of the base units. Okay, so it's units that are built out of base units. So like velocities, meters per second, and so on and so forth. All right. One thing to remember is that a cubic centimeter is equal to 1 milliliter. All right. I believe this textbook flips back and forth between cubic centimeter and milliliter, kind of just interchangeably with it. And so you just always keep that in the back of your mind when you're thinking about the volume ratios, that cubic centimeter and milliliter are equal to one another. Okay. Here's a list of the metric system prefixes. Okay. Now that you're in Chem 2, this should be like very, very, very familiar to you. Okay. All right, so in this class, I would be familiar with mega through pico. Like if you can memorize those, you're probably in pretty good shape. All right, and they kind of follow a pattern. They always go in sets of 3. 6, 3, and then you jump to -1, -2, and then 3, 6, 9, 12. Okay. Mass and length. Mass is the measure of the amount of material in an object. The SI uses the kilogram. That's bizarre, different than the gram. Okay. The length is a measure of distance. Okay, we use the meter, right, of the base unit. Volume, this is a derived unit. We kind of already talked about this. Meter times meter times meter. Okay. And then a liter is defined as 1 cubic decimeter. So if you take a meter cubed, so 1 meter cubed, and then you just take 1/100, like that's going to give you 10 by 10 by 10 decimeters. And so if you just take one of those decimeter cubes, so this little bit here, that is defined as what 1 liter is. Okay, and then 1 bit of that is 1 milliliter, right? 1,000th of that, and that's what we defined as a milliliter, and that gives us the centimeter by centimeter by centimeter. Okay. Glassware for measuring volume. So you should be pretty familiar with most of these. We've got graduated cylinder, and syringe, and then a burette. Now, all of these are graduated, meaning they have individual markings all the way along it telling you how much volume you have. Okay, but they measure kind of differently. So like graduated cylinders, you pour in from the top. Okay, and it sits there, and like if it gets to here, you got like 5. If it gets to here, you got 10, and you just kind of measure it that way. Syringes kind of work the same way, only you pull it up from here, right? And if you pull up the stopper this far, you might have 5, and then if you pull it up that far, you might have 10, etc. as you go up. Now burettes are a bit different. Remember, you pour it in from here, but then it leaves out this end. Okay, so in a burette, they go backwards, right? So you got a 0 up here, and then 1, and then 2. Remember, you're using the burette to measure how much you've poured into a beaker that's below it. Primarily, we use these for like titrations and stuff like that. Remember doing titrations? So we're going to pour that in there, okay? And then we're going to let out the solution going down this way. And so when this fluid level, or liquid level, reaches 1 milliliter, we know we've added 1 milliliter down here. Okay, and when it's gone down and it's gone to 2, we know you've added 2 milliliters down to the bottom solution, 3, etc. All right, so those guys are graduated. The next two are used to deliver a specific volume. Okay, so pipettes are these long, skinny glass tubes, and somewhere along it, they'll have a laser etched line. So it looks like on this one, the laser etched line is right there. Okay, so that's your laser etched line. So you put the end of it in solution, and you suck it up until you get your meniscus. Remember, meniscus is the guy that's shaped like this by your solution, and then so you're going to get it so it touches the laser etched line just like that. All right. And so the pipettes come in all sorts of shapes and sizes, mostly straight, but like this looks like a 1 milliliter pipette, so maybe once you suck it up it hits that line, you know you have exactly 1 milliliter. Now if you're below that line, you don't know how much you have. All you know is that you have less than 1 milliliter. Okay, if you're above that line, you don't know how much you have. You just know you have more than 1 milliliter. See how they're only really useful to measure a very specific amount. You might see volumetric pipettes that have like a bubble in the middle, like this, and that's just to kind of not make them so long and unwieldy. Okay, and for some of the big ones, like if you have a 50 milliliter pipette, you're gonna have quite a big, little glass bubble in the middle of it. And then we have volumetric flasks. Okay, these are used to make solutions because you can get a very precise amount. These also have the laser etched line on them, and they're used very similarly to these guys. You pour in your liquid. Once you fill it up, you know exactly how much you've made from there. Okay, yeah, and we use these primarily to help us make solutions. Okay, so you put in a little bit of your solvent, add your solute, okay, and then you can swirl it. Notice how it's big and fat at the bottom. It makes it really nice to make a solution. All right. Now the temperature scales, temperature is considered the hotness or coldness, and that's really not fair. Okay, we want to define temperature. Temperature is defined as the average kinetic energy of the molecules or atoms. Okay. All right, so that's really what temperature is, and that's how I want you to think of it. Not as the hotness or coldness, but as the average kinetic energy. When you stick a thermometer in a solution, you're literally letting the molecules of that solution run into the end of your thermometer, and those are exciting, giving off their kinetic energy to whatever it is that's doing the measuring, whether it be just a metal thermometer or maybe an alcohol or mercury thermometer. Okay. And you know this next part, that heat flows spontaneously from an object with a higher temperature to an object with lower temperature. That just makes sense. Heat goes from hot to cold. If it's hot outside during the summertime, it's cold inside because you got the AC on. You open the door, the hot from the outside is going to travel inside. Okay. If it's vice versa, and it's cold outside in the winter and it's hot inside, and because you got the heater on, you open the door, the heat from your house is going to leave and go outside. Okay. So anyway, here's our different scales. Okay. So starting at Celsius right here, or this little scale here, you've got water freezing right here and water boiling right here. Water boils at 212 degrees Fahrenheit, 100 degrees Celsius, and 373 Kelvin. And then water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, and 273 Kelvin. All right. So in science, we use Celsius and Kelvin because they're easy to use. All right, it's really easy to think to yourself, oh, Celsius, 0 degrees Celsius is water freezing. That makes it super handy. Okay. We also use Kelvin because Kelvin is defined that 0 Kelvin is absolute zero. I think we talk about that here in a minute. And so that means when we're doing calculations involving temperature, we never have to worry about getting a negative temperature when we're using Kelvin. Okay. So the Kelvin is the SI unit. So that's the one when we do our gas laws and other things, we're always going to go to Kelvin. Okay. And it's based on the properties of gases. There are no negatives. The lowest possible temperature is called absolute zero. So in order to convert from Celsius to Kelvin, we use this value. I expect you to memorize that right there. 273.15. Right? Now Fahrenheit is not used, but you'll hear it a lot from everybody else that's not as sophisticated as us. Okay, these are the equations that you need to use, all right, to calculate from Celsius to Fahrenheit. I won't expect you to memorize those. I probably won't ever expect you to use them in an exam, but those are the equations. So if you're doing it, there are several homework problems that you have to do it. So if you have to do it on the homework assignment, honestly, I'd probably just go to Google and ask it to convert it for you. All right, I found this. I thought it was pretty funny. that, like, in Fahrenheit scale, if it's 0 degrees, it's really cold outside. That's pretty chilly. And if it's 100 degrees, it's really hot outside. That's a pretty warm day. In Celsius, if it's 0 degrees, it's fairly cold outside. But if it's 100 degrees Celsius, well, you're dead, because that means all the water in your body is boiling. Yeah, that's no good. It'd be pretty painful. In Kelvin, at 0 degrees or 0 Kelvin, you'd be dead because it's absolute zero. All of the motion of your molecules is stopped. Okay, and then at 100 Kelvin, you'd also be dead because that's still stupid cold, right? 100 Kelvin is like negative 173 Celsius. Okay, it's pretty cold. All right, energy, this is just talking about more derived units that we might run into throughout the year in chemistry. Okay, so the joule is the unit of energy. It is a derived unit. And here they go through deriving it for you. So a joule is equal to 1 kilogram per meter squared per second squared. All right, and it's all related to this idea of what kinetic energy is. I don't really care if you know how to derive it, but you should be familiar with what are the base units it's made out of. Okay, we commonly use kilojoules for chemical change, just because chemical changes, you produce and use so much energy, and a joule is actually fairly small. Okay, if you're reading old school textbooks, they might refer to it as the calorie. And a calorie is equal to 4.184 joules. So a lot of times you go ahead and use this relationship because it kind of is useful when you're looking at a little bit older data. Okay. Note that the normal calorie is not the same as the nutritional calorie. Nutritional calorie has a capital C, lowercase calorie. Is not. So 1 capital C calorie is equal to 1,000 lowercase c calories. All right. Density is a physical property, right? It's something that we can use to identify things. Okay. And it has units that are derived as well. Most common are these guys here, grams per milliliter and grams per centimeter cubed. Okay. Your first unit or your first lab that you're going to have in just a couple of days, you're going to design a lab to determine whether or not density is an intensive or extensive property. Okay. Other numbers that are encountered, you have exact numbers. Okay. Exact numbers are numbers that are given by definition or are counted. Okay. So, for example, there are 12 eggs in a dozen. All right, this is a defined value. We have defined as a human society, if somebody says they have a dozen something, that means they have 12. Unless for some reason bakers get an exception to this. And if you have a baker's dozen of something, then you have 13 of it. I don't understand. But anyway, so if it's a defined value, so like as a society, we've decided that there's 12 inches in 1 foot. That's a defined value. So the 12 inches in 1 foot, if you use that in a calculation, that is an exact number. Okay. Now, counted numbers are also exact. So there's 19 students in the class. There's no difference in saying there's 19 students or 19.0 students or 19.00 students or 19.000 or 19.000000 or etc. Right? They're all the same because there's 19 students. All right, so that is also an exact number because you've counted it. Okay, inexact numbers are measured numbers, and that's the key. So if you have to measure it, not count it, if you have to measure it, you have to use some device to measure it, either like a balance or a ruler or a thermometer or anything like that, then that is a measured number, and that is going to give you an inexact number. All right, and so this is where this next part comes in about uncertainty. Okay, so when we're measuring things, we're going to have some certain amount of uncertainty. Okay, different measuring devices have different uses and then therefore different degrees of accuracy. Okay, so so a ruler that has lots of little lines in it is going to be a lot more accurate than a ruler that only has 1 line for every inch. Okay, it doesn't matter what you're using. Okay, every measured number is going to have some value of inaccuracy. Doesn't matter. Okay. So therefore, the last digit is always considered reliable but not exact, or an estimated digit. Okay. For example, on this thermometer, there's 20 and so that's got to be 30, right? So we're between 20 and 30 right here. They've zoomed in for us. But notice that there's no individual lines. So we know for sure that we're somewhere between 20 and 30 for our reading. Now, we can estimate one more digit than what is given on our mechanism that we're reading. So we've got this one for sure, the tens place. So we have to estimate in the ones place. So they estimated, oh, there's the fives places as well. So we know that we're somewhere happily between 25 and 30. Okay? Because you can see there's the little hash marks between. So there's 20, there's 30. So then that guy there is 25. So they've zoomed in here, and it looks like, you could, and then at that point we're just estimating. So this is 25, that's 30, 39, 38, 37, 36, 35. I screwed it up, didn't I? Whatever. So anyway, so they estimated it to be at about 27 degrees Celsius. So therefore, if you were using this value, you knew that this 2 was exact and reliable, okay? But the 7 was not reliable. It's an estimation. All right. Now, accuracy versus precision. This should be like double review, okay? Chemistry, we talk about it. Physics, we talk about it. Chem 2, we talk about it again. Okay, precision is a measure of how closely your measurements agree to one another. Okay, if I stand on my bathroom scale and it tells me that I weigh 200 pounds every time I stand on it, then that thing is very precise. But if I go to another scale that I know for sure is correct and it tells me I actually weigh 210 pounds, then my original scale is not accurate. Accuracy is how close you are to the right value. Okay? So precision is how much your things agree with one another, and accuracy is how much you agree with what should be the answer you got, okay, or the true value. All right. So this guy here, we can kind of learn it by picturing it in regards to a target. All right. So because they hit the bullseye each time, they had good accuracy and good precision. This guy here, they had poor accuracy. They didn't get anywhere close to the target. All right, this is kind of like my bathroom scale. Oh my goodness. All right, they didn't get anywhere close to the bullseye, right? And the darts are over here, but they're all close together, so therefore it has good precision. Down here, they totally whiffed the board. They got in the gray, like, well, I guess this one might be in the red, so this one. But regardless, they did not do well. Okay, and they didn't really get close to the bullseye, so therefore it's not very accurate, and they kind of like, this one's way off to the left, way off to the right, way too high, so therefore it's got poor precision as well. Okay, now here's the idea. We're talking about uncertainty in measurements, and we know that the last digit has always been estimated. So in science, when we combine science with math, we need to be able to keep track of where that estimated digit is. Okay, and that allows us to make decisions based on what's going on. So we call this keeping track of the estimated digits significant figures. These are the numbers that help us keep track of the estimation. Okay, so here's the rules to significant figures. All non-zero digits are significant. Zeros between non-zero digits are significant. So sometimes these are called sandwiched zeros. So so for example, if we have 1, 2, 3, this has 3 sig figs. Okay, if you have 1, 0, 1, this has 3 sig figs, right? Because the 1 is significant, so is that one, and then because that 0 is between two ones, it's sandwiched, so therefore it is significant. Okay, zeros at the beginning of a number are never significant. So if you have 0.100, it's too complicated an example. If we have 0.001 as our number to start with, okay, all of these numbers are leading zeros. They're not significant, so this number has 1 sig fig. Okay, then zeros at the end of a number are significant if it contains a decimal point, and that's the key. Okay, so let's look at some of these examples down here. Okay, so 1.03 times 10 to the fourth. So this is a sandwich 0, so therefore it's got 3 sig figs, right? The 1 and the 3 are significant. The sandwich 0 is significant. All right, how about this guy? Now, it's so we got 1 is significant, the 0 is still sandwiched, the 3 is significant. Now, 0 is at the end of a number, and number 4 says the zeros at the end of a number are significant if it contains a decimal point. Well, this has a decimal point, so we'll go ahead and include that one, so therefore it's got 4 sig figs. And then finally, same idea as the first one, we've just tacked on another 0. There's still a decimal point, so we got 5 sig figs. All right. When you're adding and subtracting sig figs, you're always going to keep track of where your decimal place and round your answer to the least significant decimal place. Okay. Did I remember to include? All right, so let's do a couple of practice problems here. So if you have 902.34 and 50.1, and you're going to add these guys together, what I want you to do is you're just going to add them together like normal and write out your answer. You're going to say, all right, that's 52.44. Okay. Now, you have to figure out where the least significant decimal place is. Well, the least significant decimal place is this 1 on that 50.1. Right? That's the least significant. So therefore, I can't have my answer be any farther to the right than that. So draw like a little light line across that point, and your answer is going to be 52.4. And then you have to decide, all right, does that 4 round up? Well, that 4, the next number is a 4, so that's not 5 or greater, so it doesn't round up. So the real answer would be 52.4. All right? And the same thing works for subtraction. You line up the decimal points, and Bob's your uncle. All right. When multiplication or division is performed, answers are rounded to the same number of digits as the measurement with the fewest number of sig figs. Okay, the fewest number of sig figs. So let's say we take 50 or 5 times 12. Okay, and that's our values here. Well, 5 has 1 sig fig. 12 has 2 sig figs. Okay, so our answer can only have 1 sig fig. Okay, so our answer is 60. Okay, and that'd be the right answer. Now, what if we had 5.0 times 12? Okay, well, each of these has 2 sig figs, right? That's got 2 and that's got 2. So therefore, our answer has to have 2. So when we write it, we'd have to include that decimal point. Okay. Now here's the trick. When you're doing this, never, ever, 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 ever round early. Okay? You got to keep track of your sig figs throughout the whole thing, but don't ever round early. Just, if you round early, you'll probably end up with a mistake. Okay? Now, last bit here, dimensional analysis is used when we change units. Okay? By Chem 2, you should be super familiar with this, but we're just going to do a couple of problems real quick. Okay, there are directions here. You can read through them on your own, but I kind of find them confusing. So let's just do a practice problem together. It says the average speed of a nitrogen molecule in air at 25 degrees Celsius is 515 meters per second. And it says convert this speed into miles per hour. All right, so we're starting with 515 meters per second. Okay, and we need to get it to miles per hour. All right. So we're going to convert our meters to miles and our seconds to hours. All right. So let's see. So we've got meters on top, so we're going to put meters on the bottom so they cancel. Let's see. Do they give us a ratio? Yes, they do. Okay. For every 1 inch, there's 2.54 centimeters. Okay. So we got to get meters to centimeters so we can use that conversion factor. So we'll put centimeters up top. All right, for every 1 meter, there's 100 centimeters. Okay, so now I'm in centimeters. All right, now I got to convert my centimeters to inches. So my centimeters, I'm going to put them in the bottom, and we know that there are 2.54 centimeters for every 1 inch. All right, so now I'm in inches, and then I got to get to miles, right, because we got to get miles per hour. All right, so we got to do at least 2 more conversions. So inches are going to go on the bottom, feet are going to go on the top. For every 1 foot, there's 12 inches. And then, finally, there's 5,280 feet for every 1 mile. All right? So far, if I did all that math out, my units would be thus. My meters would cancel with meters, my centimeters would cancel with centimeters, my inches would cancel with inches, and my feet would cancel with feet. So I'd be left with miles per second. Okay? That's what I'm at right now. I'm in miles per second. I've kind of run out of room, so I'm going to go ahead and solve for that and put into that unit. So remember, the top values you multiply, the bottom values you divide. So we'll take 515 times 100 divided by 2.54 divided by 12 divided by 5,280. and I got 0.320000616. Okay, now remember, we're not going to round for sig figs yet because we're not at our final answer. So 0.320000616. Or you can just, obviously, you wouldn't stop here on a regular test. You'd probably keep going, but I just ran out of room. Okay, and remember our units here are now in miles per second. Okay, so still our nitrogen molecule is moving like 1/3 of a mile every second. Holy cow, that's pretty dang fast. All right, so now we got to get it into hours. All right, so we're going to convert our seconds to hours. So we're going to put seconds at top. Well, remember before the meters went on the bottom because I needed them to cancel because the meters were originally on top. Now my seconds are on bottom, so I got to put my seconds on top so that they cancel. Okay, so my seconds are going to go on top. Then I'm going to go to minutes. Okay, and I know there are 60 seconds for every 1 minute. All right, and then I'm going to put minutes on top and hours on the bottom, and I know there's 60 minutes for every 1 hour. All right, so I'm going to take my original answer, multiply it by 60 times 60, or 3,600, and I get 1152.02. 1152.02, and my units are miles per hour. But we got to think about sig figs for a second. So we got to go back to what we started with. All right, so we've got two numbers up here. We've got 25 degrees Celsius, okay, but we didn't use that number, so we're not going to use it to help us figure out our sig figs. The other value we have is this guy here, the 515. That's what we started with. Now, how many sig figs does that have? Well, that has 3 sig figs, so that means my answer can only have 3 sig figs. So I got to look at my answer, count 3 sig figs from the left, and that's where I have to stop rounding. Okay, so I go 1, 2, 3, I stop at the 5, so I decide, does the 2 make the 5 round up? No, it does not, so therefore my answer is 1150 miles per hour. In other words, nitrogen molecules move pretty dang fast, all things considered. That is the end of the slide. Okay, this is a fun little video you could watch, download it from the Google Classroom and all that jazz. Anyway, do the homework problems. Let me know if you have any questions, and I'll see you in Chapter 2.